Okay, this is a review of what we did in class in case it wasn't very clear for the folks at home. Again, this is a review of kinematics. The goal is to remind you of the things you've learned previously in earlier courses about kinematics, and then you'll get some practice solving some problems, and then taking a look at position time, velocity time, and acceleration time graphs. So we reviewed that vectors are things with both magnitude and direction. Magnitude meaning the size, and direction, which way they're going. So displacement, which we said was change in position. Change in position is one, whereas distance is a scalar. A scalar is something that has magnitude only, no direction. And then we spent some time talking about the difference between distance and displacement. Speed, which is the time rate of change of distance, is also a scalar, has no direction, while velocity, which we talked about, average velocity, is the time rate of change of, or in fact, any velocity is the time rate of change of position. This is the definition of average velocity, and then later we saw that if you put a limit sign in front of it, take very small time intervals, you get instantaneous velocity. And acceleration is the rate of change, the time rate of change of velocity. We also talked a little bit about these different symbols that you might see this year. I like to use delta x for displacement, but often you'll see delta d as well. The IB gets rid of the delta completely and just gives it an s, which can sometimes throw you off a bit. This didn't come out. This also has a delta. Delta t we use for elapsed time. Remember, any time you see a delta, it means final minus initial. So this is t2 minus t1, or t final minus t initial. That's something to keep in mind. The IB gets rid of the delta and just calls it t. Again, that's a bit confusing. V2 becomes just v, and v1 gets a u to distinguish it. So that would mean that delta v, which is v2 minus v1, by the IB would be written v minus u. So just a few things to keep in mind. Again, we said that velocity is the time rate of change of position, and acceleration is the time rate of change of velocity. Okay, then we talked about average velocity, and we said that the definition of average velocity is, to use the notation that I would prefer, delta x over delta t. That's the change in position over the change in time. Remember that we said that the IB will call this s over t. So that's average velocity. You take the elapsed, or you take, the change in position divided by the elapsed time. Again, that's equal to position 2 minus position 1. Position itself is a vector because it's relative to the origin. You want to know, are you to the right, to the left, to the north, to the south? T2 minus T1. So average velocity is change in position over change in time. Then we did a little bit of an illustration with the moving man simulation, and we talked about how if you graph position versus time, then you can imagine your person walking along up and down this x-axis. We've tipped the x-axis on its side so that we can have time on the horizontal axis. And so if we track up like this, along here, like that, the person is moving up that line. Okay, that can be helpful to keep in mind with position time graphs. That means that in this phase here, now the person's not moving, now they're moving back towards where they started and overshooting and going backwards. Okay, so that's what we did in this part, looking at the moving man. Now, if this is the definition of average velocity, and we want to know the instantaneous velocity would be, imagine you had a speedometer that could go in the positive and negative directions if you're going backwards, so this would be going forwards fast, this would be going backwards fast, and this would be at 0, not going anywhere. So if we wanted to know the speedometer reading on this person, we don't want to know the average velocity, we want to know the instantaneous velocity. And if it's actually a graph like this, where we have constant velocity, because velocity is the slope of a position time graph, then average and instantaneous are the same. So v average equals v instantaneous if v is constant. Okay, so that's a special case here, but in all cases we talked about taking very small time slices. The calculus notation for this is the limit as the time interval goes to 0 of, and then it's just exactly the same thing as we had before. Change in position, which we also call displacement, over change in time. Remember that the IB is going to call this S, and it's going to call this T. Okay, so that was what we talked about with average and instantaneous velocity. On a position time graph, then, if we have position on the x-axis and time, position on the y-axis and time on the x-axis, let's say we have a graph that looks like this. We talked about how this is the graph of something that is accelerating because the slopes are changing. If I draw a line from one part of the curve to the other, which we call the secant, then the slope of that line is the average velocity over that time interval. If this is time 1 and this is time 2, this is therefore position 1, and over here we have position 2, then I want to know x2 minus x1, that was my numerator, that becomes the rise of this line. And I want to know t2 minus t1, that becomes the run of this line. So they are, again, x2 minus x1 over t2 minus t1 is going to give me the slope of that line. And so the average velocity is the slope of the secant. If I want the instantaneous velocity, I have to bring those points closer and closer together until they touch. And if you imagine sliding this one left and sliding this one right, you will eventually end up with a tangent like that. And the slope of the tangent is the instantaneous velocity. Carrying on, acceleration just takes the whole process one further step. So average acceleration is equal to change in velocity over change in time, which is v2 minus v1 over t2 minus t1. Again, if we want instantaneous acceleration, we take the limit as time goes to 0, meaning we take a very small time interval over which we calculate the change in velocity. Now, we also talked about how whenever velocity is changing, there's acceleration, but that does not mean that the object is speeding up or slowing down, because acceleration happens when velocity is changing. Velocity has two parts. It has a magnitude and it has a direction. And it's often easy to see, or it's intuitive to see, when the magnitude of the velocity, meaning the speed, is changing. There's acceleration, but you need to be mindful that if the direction is changing, then you've also got acceleration. And the example that we looked at was circular motion. Even if you're moving in a circle at constant speed, you're changing direction, so your velocity is changing, so you're accelerating. As we'll see later in the course, or as we'll review later in the course, if there's acceleration, there's an unbalanced, non-zero net external force. That's kind of Newton's first and second laws. If we graph a velocity time graph, and if we have the same kind of shape, let's say, as we did before, then now the slope of the secant is the average acceleration, and the slope of a tangent, imagine that's touching, is the instantaneous acceleration. Okay. We also can find the area under this curve, and the area under this curve, I'm going to write AUC for area under the curve. The area under the curve of a velocity time graph gives me the displacement. So area under the curve of a velocity time graph gives me the change in position, or the displacement. We'll come back to these in a second. In summary then, on a position time graph, the slope gives me the velocity. the slope of the secant if I want average velocity, slope of the tangent if I want instantaneous velocity. On a velocity time graph, the slope gives me the acceleration. Similarly, average is the secant, instantaneous is the tangent. On a position time graph, we're not going to be calculating acceleration. On a position time graph, the displacement is just the change in the y values being the positions. Remember, displacement means change in position. So it's a change in the y values, not just the y values. Another way of thinking about that is it's the rise of the rise over run. On a velocity time graph, velocity is just the y values. That's what's on the y-axis. Displacement, we just said, is the area under the curve. And it's in fact the signed area under the curve. If it's above the x-axis or above the time axis, it's a positive displacement. And if it's below, then it's a negative displacement. And we looked at examples like this, where, let's say, this is +5 and this is -3 and this is velocity and this is time. The area under that is 5 minus 3 would be +2 meters. Again, this time is in units of seconds, velocity is in units of meters per second, so the area of each of these rectangles is meters per second times seconds, which is meters. So the area under the curve of a velocity time graph is the displacement. We don't find displacement from an acceleration time graph. From an acceleration time graph, on an acceleration time graph, the acceleration is the y values. And similarly here, going backwards from here to here, going backwards, similarly to here, on a velocity time graph, the signed area under the curve is the displacement. Here, the signed area under an acceleration time graph is the change in velocity, not actually just the velocity. So the signed area under the curve is the change in velocity. Just like here, the change in position, the displacement, is the signed area under the curve. Okay, then there are these equations of constant acceleration. You'll get them in your formula booklet. Just note that some of the symbols are different because the IB changes things out, right? They write t instead of delta t. They use s instead of either delta x or delta d, as you might be familiar with, and they use v and u. These are just a matter of identifying which variables you have and which ones you need, and then solving. And we'll do some practice with that. Okay, so that's a quick review of the material that we covered in class in case it was unclear on the video at home.